Everybody, another problem that seems almost impossible when you first read it, and this is what I'm trying to convey here by juxtaposition. You just have a bunch of digits next to each other, and in this case we have 60 of the digits 9. Okay, and we're raising it to the 7th power. Now, I know you guys know this, but 999, for example, is equal to 10 cubed minus 1, right? And so there's a relationship between this exponent 3 and the number of digits, okay? So I've rewritten it this way for hopefully for obvious reasons that we can appeal to the binomial theorem here, okay? So we're going to work it for the general case, actually. And what we're going to do would actually work whether it's n is 60, n is 400 or whatever, okay? It would work for every single case. Now, so this is the binomial expansion. This right here is 7 choose. For example, this would be 21 is what? 7 choose 2? Okay, and the 2 is actually getting applied to the -1, which would square it, which is where the positive sign comes from. I didn't show all the steps, but this is the binomial expansion for our value, for the general case. And when we're done with this, we'll just substitute n equals 60 into this. Okay, that's the idea. It's one of these problems where it seems to be easier just to do the general case rather than a specific case. Maybe I'm wrong, but it just seems like a nicer way to do it. Now, so the big trick here is to group these into groups of 2. Notice how we have 10 times 6 to the n, 10 times 4 to the n after you do the factoring, 10 times 2 to the n. Remember, 10 raised to any power is not going to add any 9s to things. It's just going to tag on a 6 to the 6 n zeros. Okay, so this would be responsible for 6 n zeros attached to this object. It won't affect the number of 9s. Now, let's work. I'm just going to work one of the cases here, folks. The one maybe perhaps the most difficult one. We're trying to find out how many 9s are in each one of these groupings here. We have 1, 2, 3, 4 groupings. Now it's pretty obvious right here that this contributes n 9s. I'm going to write it like this, folks, n 9s, n digits, 9. And you can see that very clearly, right? The very first one would be what, 69 for n equals 1. There's 1 9, right? And then if you do n equals 2, you get, what, 99? Okay. And then so on, n equals 3, you would get 999. Right? Or let's see, is that right? Yeah, 7 times, no, this would be 699 right here, right? For n equals 2. Right? Because this would be 700 minus 1. And then so on, n equals 3, you would get 69999, right? So it's very clear that there are n 9s in this expression right here. In each term in this is of course n equals 1, n equals 2, n equals 3, right? So that's clear enough. So just this part alone contributes n 9s. All right. Now let's take a look at one that's perhaps slightly harder. This case right here, 10 to the 4n. Now again, the 10 to the 4n is really kind of just inert as far as what we're trying to do. It has no impact on the number of 9s, only how large the number actually is. It just kind of pads it with zeros. Now, the very first one here for n equals 1, what would we get there, folks? 2065. For n equals 1, this would be 21. Yeah, this would be 2065. And again, folks, I'm just substituting n equals 1 right here. Now, for n equals 2, I got 20... oh, no. This is for n equals 2. My bad. This would be n equals 2. For n equals 2, we get the number 2065. And for 1, I didn't write it down, but we don't get any 9s, okay? Now, for n equals 3, for n equals 3, we end up getting 22965. You're having to borrow from one of the positions there. Borrow power of 10. For n equals 4. Okay, for n equals 4, we get 20, and then a pair of 9. So you see, you can kind of tell what's going on at this stage. This would be a 9965. Like that. Okay. But so you see right here, folks, we have 2 9s right here, and then we have 1 9 right here. And I think I got the arithmetic going. 20, 9965. So y'all, you can see right here that this term would contribute n minus 2 9s. Because you have to get, when we get to n equals 4, when we get to n equals 4, there are 2 9s, right? 4 minus 2, there's 2 9s. When n is equal to 3, we get 3 minus 2, which is 1 9, right? So you see this one alone, and I won't go through all the rest of them, but so far we have this, and this, and the other two are slightly easier, I would say. This one actually, and you guys can verify, contributes n minus 1 9s. Okay, so that's our third one. And this very first one is the very same thing. It contributes n minus 1 9s. Okay. So y'all, here we go. These are the 4 contributions, and everything is so spaced out by the powers of 10. There's no overlap here, if you're wondering about that. Okay, that raising 10 to a power, and then there's gobs of zeros if you actually use something like Python or something to do this. Okay, but notice we have to sum up these 4 objects here because they are mutually exclusive. All right, so this would be, we got an n here, an n here, an n here, so that's 4n. So overall we have 4n, and how many constants do we have? We have minus 1, minus 2, and minus 4, right? No constants with this, so we have 4n minus 4 9s. Okay, and so what is that? That's equal to 4 times n minus 1. And again, this is the general case, folks. So we have 4 times n minus 1. So I could have worked this problem just the general case. I just happened to work, I wanted to work the special case. But, so there's 4, like that, okay? So what do we got? So how many digits? That would be, so we're doing n equals 60 here. So that would give us 4 times, what is it, 4 times n minus 1? So that would be 4 times 60 minus 1 equals to 4 times 59. 4 times 59. And you know, that I'm getting 236. And I would like somebody to, if somebody can code some Python or something, whatever you want to write up, see if this is right. Obviously, it's an immense calculation, but there's 236 9s according to what I'm doing here. But it feels right, and I don't think I made mistakes, but you always say that anytime you're doing all these computations, you may have overlooked something, or actually I may have done the binomial expansion wrong. But this is the answer I got, folks. 236 9s are what happens when you raise 9,9,9,9,960 times to the 7th power. Okay, so that is all she wrote, folks. 236. And yeah, back down here is where we did the work. Okay, I like that problem. It's some sort of SMO problem, by the way. I think it's an SMO senior problem, something similar to this. Okay, good day.